Good morning, ladies and gentlemen. I'm Neil Walker, liaison in Washington, D.C., and I'm here to talk to you about support vector machines. This is going to be an introduction, so I'm going to try and keep it at a high level to see why you might be interested in it, and hopefully can interest you more in diving into some of the possibilities. So support vector machines are a way of classifying data. So they can handle really any sort of classification problem, and actually even be used for regression in some instances. So right here, we can look at how a computer might see data or visualize it. And if I was to ask you to divide these into classes, I think you can very intuitively and quickly figure out exactly where you might want to draw a line to do that. And that's a question we can ask a computer. If this was, for example, cats and dogs, the wonderful classification problem that everyone looks at, perhaps the bottom would be the length of the size of the dog cat, and this axis here could represent the pointiness of ears. See, I don't know a lot about the differences between cats and dogs, which is slightly why I'm interested in classification problems, getting computers to help me. If we just asked it to do to draw a line, might pick this line. And it is, of course, technically correct, but you might intuitively think, well, why did it put it there? And is that the best place? Because if we run into another animal, another dog, for example, it would classify that as a cat based on that line, and of course be wrong. And the computer needs a way to figure out where to put this line. So there's a lot of different space that it can do so, and it will keep misclassifying. So what we're looking for is, of course, this line, which creates the optimal amount of space between the two classes, which we would call the maximum margin. And that way it will be the best at predicting things, or the best we can get based on the data that we give the computer. Ta-da, both of them correct. So, really simply, support vector machines are used to classify data into groups, two groups, and it does so by finding a line between the two groups. It can work in multiple dimensions, and so that would be a plane or a hyperplane in higher dimensions. But it is built on this idea of the maximum margin classifier. So if we look at this is basically the algorithm that the computer will be using to increase, decrease the margin, and rotate it and move it between the two classes in order to find the largest gap. So, great, perfect. This is what we want to find, this is what we want to look for. These are what are the actual support vectors in the support vector machine. They are the closest points to the other class, and it uses these points to identify the margin lines, and that's just what is the basis of the calculation and where this model gets its name. So, what do we do when we run into a class like this? This is what we would call sort of an example of a mixed class. We've added some more cats and dogs to our model, and we can no longer draw a straight line, or at least the computer can't, because of these classes, because we threw in a Chihuahua and a leopard. I don't know, some cat that looks kind of like a dog. We have to train the model a little bit more, and we basically can modify it to ignore some examples. This actually turns out to be super helpful. In this example, we just tell it to ignore 2, and that can be increased. But it's going to help us with a lot of other issues, such as overfitting, where our model, if we had the Chihuahua in the example, I think actually we'll show it here, but yeah, if we have, say, the Chihuahua in the example, this is going to push our line from the machine, our maximum margin. This is going to be accounting for that, and that's what we call an outlier, something that kind of messes up our model. So we would want to, even in an example where the classes are not mixed, we might still want to use the support vector machine over just the maximum margin classifier, so that we can still get a good line. Because this would end up misclassifying a bunch of cats later when we start actually doing predictions. And because of where it pushed. Whereas the normal line would only misclassify the one Chihuahua. I don't like Chihuahuas much. This is just a visualization to show that the same type of idea can be expounded upon into 3 dimensions. And I had a 4-dimensional picture, but it broke my computer. So it was unfortunate. I had to get a new one. All right. So here is another example of where we still run into issues even dealing with mixed classes. Right now, if we only have one piece of information, maybe it's how dark the color of the fur is or something. So you have a number of dogs with light fur and a couple with dark fur, and then these other, we'll go with a breed of dog, just have kind of gray. So that's the only piece of information you have for the computer to guess. And we ask it to draw a line. It can do that. We can misclassify a couple. It can actually draw lines in a number of ways to misclassify, but we're never going to get a really good answer. So how do we go about dealing with that? Well, there's the real trick behind the support vector machines is we're allowed to modify our data. So even though we only know the darkness of the fur, we can actually feed 2 pieces of information essentially to the computer. We can feed the actual darkness, and then in this example we'll just be squaring it. So we give it 2 pieces of information, how dark the fur is, and then just the exact same piece of information, which to us doesn't really give us anything more, but for the computer, we can now draw a nice line that classifies our data. And that's essentially the magic behind support vector machines. Right, so we call this the kernel trick, and it's based on mathematics that essentially look at further dimensions in our data in order to create nice smooth lines. This is an example where that could be a problem. Obviously, there's just no possible way to draw any number of lines that could divide this data, but the support vector machine is able to not do anything at all, apparently. No! That was a cool one, too. I don't know why it's not running. No, that depresses me. Oh, yeah. There we go. All right. Isn't that really cool? So it's able to fold the data essentially into a 3rd dimension. This is 2D. And then it finds a plane that can split it in half. I mean, if the YouTube videos don't work, why even tell those guys, you know? Anyway. So these are a couple of examples of kernels that we can use, and they essentially, by using multiple dimensions, they're able to divide the data up. You can actually see the support vectors are these slightly darker dots. Those are the dots that are making our boundaries. This is a polynomial kernel. This is a radial. You can kind of almost see how it radiates from, it does use more vectors to create these boundary lines, which can be slightly more processing intensive, but yeah. So this kind of technology is super useful in really any sort of type of classification problem. We can, send a large number of amount of data, which we can think about as our dimensions, and it can add more to help divide that in ways that we might not otherwise be able to. So it can be used for facial recognition, image classification, text classification. There's also financial and even medical applications. I did want to acknowledge my YouTube videos that I took some of the images. And Eric Kim, he has some really great articles that help bring the kernel trick down to earth. And we can go into that a little bit more if you have any questions. Thank you very much. Yes?
Can you have the 3D presentation where you show you draw the line?
Drew a lot of lines.
The
The one with the graph?
yes, and you have like the gray lines on either side.
I think that's all. Yes.
Yes. Is there any? Does the space between that trend line and the gray mean anything, or is that just?
That is that's the maximum margin. So that's what we're trying to increase. So basically the algorithm is looking through, it has to look at multiple points, and then it finds the points where we can create this as the largest, which gives us the best sort of margin of error for additional predictions that the computer is trying to make, data that we don't have to give it yet.
Thank you.
Sure. Yeah.
Could you go a little side forward to the one that you used, to the one that you separated with the support vector machine?
Yeah. This one?
No, over. Like the round one. Yeah. I guess with that, didn't you just use like polar coordinates to do that?
Use, I'm sorry?
Polar coordinates to do that because all the, it seems like they're like a circle would just work to separate the roof from right there.
So it's, I'm honestly not sure. I mean, there might be other models that can do that. And really, this was just a sort of example to get a cool image in. No, to show that the support vector machine, you might not necessarily be able to see your data.
Okay.
So if we're only having really two pieces of information. So when you're actually talking about, real data sets we're talking about many dimensions. So it's not going to be something you can visualize and intuitively do. So we need to find a way for the computer
Okay,
to.
gotcha.
So,
That makes sense.
sir.
Just explain how you might use this to classify something into more than two classes.
There's more. So yes. So the kernel trick uses the ability to draw a line or plane, hyperplane, to divide classes into two. You can do what's sort of called an all versus one, or like one class versus the rest to draw a line, and then look at another class, and then draw a line that divides it. So you can actually, it's essentially just dividing two into two, but by doing it multiple times over, you're able to divide into any number of classes. Good question.
So am I right to assume that this model won't be very helpful if your data points are mixed properly? Like here you can still see like a circle as a pattern, and even in your previous slide you can see them quite separate, but if there was a lot of overlap between them, then what would you do in that situation?
So if the data was completely overlapped,
Yeah.
you're probably not going to, you probably don't have enough information to make accurate predictions.
Yeah.
If you use actually the radial-based function, it can get down to exact dividing on each point, but you're not going to get good
Then you have
predictions.
overfitting.
Yeah, you don't really have enough information.
Understood.
Yeah.
Okay. Thank you.
Sweet, thank you.